All right, welcome everyone. This is the 9th zkWarsaw Meetup, and it is the first after our full-day conference, the zkWarsaw Day. So thank you so much for being here. It's the first time in this location, so please bear with us with all of the logistics and pathfinding challenges. We will be getting better over time. Now, the topic for today's...
Before you go for the topic, remember what is after the presentation.
Yes, so the structure for this meetup today will be, we will have a presentation by Adam here from Aztec. And within 1.5 hours, we will be moving to a more informal part with some drinks outside. I think Marek reserved a nice place just outside the door over there. So the format for today is going to be, Adam will be guiding us through the Aztec Sandbox, but he kindly offered to take questions as we go, and we are trying to keep this an informal conversation already. It's just that we are recording today, so keep that in mind. And it would be great if you have a question, if you could grab this mic so that people who are watching can follow afterwards. Any questions? Okay, cool. So, welcome, Adam.
Thanks so much. I'm Adam Domurad. I'm a software engineer at Aztec. I'm going to be talking about the Aztec Sandbox, which is a sort of self-contained prototype environment of the Aztec network. Everything in the Aztec Sandbox aims to be like mainnet launch of the Aztec rollup on Ethereum, but cutting every corner we can to get this in the hands of people, getting feedback on the UX, having people iterate on the development experience. Next, please. Okay, so as I said, it's a local developer environment, runs entirely on your computer. I'll be going into what you can do with it, which is approximately what you're going to be able to do with the main Aztec network. And at the end, I prepared a bit of behind-the-scenes details on what's going on in the Aztec network. Next slide. So the talk is basically in 4 parts. First, the different action types and state management. So namely, public and private state. They're intertwined in Aztec. And I'll go into why we need both and how we achieve this. Native account abstraction. This is a powerful feature in Aztec network that allows any private function to be the entry point of a transaction flow. It means that we're not baking in the same assumptions that Ethereum does, that we're not requiring you to first go through some predetermined authorization flow. Actually, you can determine it with any zk logic programmed in our framework. And this lets you do things like Touch ID or Web2 authentication, or like maybe you want to authenticate a passport, crazy stuff like that. Then we have L1 to L2 messaging that I'm going to talk about a bit. It's essentially what Aztec, I would describe it as. Aztec itself is just a message box on Ethereum. Everything connecting with Ethereum uses L1 to L2 messaging. And what this lets you do is it lets you do everything from connect to Ethereum smart contracts to define asset bridges. And there's actually no native assets on Aztec. So this is an important part of connecting it to Ethereum. Yep.
Quick question. What does it mean there's no native assets? You don't issue anything other than bridging?
We are completely, the rollup contract is just a message passing zk provable contract that can connect to other contracts through the L1 to L2 bus. So there's not even actually a native Ethereum on Aztec. We're completely just building a neutral message passing layer that enables privacy and public states, but everything is by the community, basically. Then the last part, I'll be going to Aztec Noir, which is the smart contract framework that's used to code both public and private state transitions in Aztec. Next. Okay, so just very simply, we support 2 types of functions in Aztec. In public, you can very much think of similar to Ethereum. We do not have an EVM model, we kind of break from EVM. We do stuff like native account abstraction, and we also provide a model that's uniform across our public and private functionality, tailored towards doing efficient zk proofs, and for a user experience that's kind of we kind of feel, once you do enough small breaks from EVM, you might as well just rethink the user experience. But in broad terms, the public state is very much like Ethereum. The private state, however, is thought out from the ground up as a programming model that is something you cannot do in Ethereum. It is based on notes, UTXOs, kind of more like Zcash. And it has a programming model that lets you prove privately on your own device anything that happens with a zk proof. And we have a domain-specific framework, so it's built on our language Noir, that aims to kind of make the complexities of zk adjacent to the actual logic. So it's kind of a plug-and-play framework that can support different provers. And it's meant to abstract away zk while having a more programmatic model than stuff like zircon or previous programming languages, which I'll go into more. Next. All right. This is where it gets a little annoying. If you could just put just next until all the text is on the screen. Okay, good. So there's two types. So the paradigm is both private and public execution. So private execution, entirely on your device, zk proofs. Public execution, also zero knowledge proofs. So maybe I'll just talk very briefly about this as a zk meetup, but just very broadly. So the zk proof means that when we are talking to Ethereum, all we're posting is the old state hash and the new state hash, and a very succinct proof, a snark in this case, that those two have a valid state transition. For the private execution, the user is doing that by themselves. The goal is for someone on their phone. This is something that was possible in our previous product, Aztec Connect, but we kind of have more ambitions here to do a general rollup on their phone to be able to privately prove their state, and no one else sees it. You prove your state transition entirely locally, while the public state, which allows for shared state, which the private state does not. The private state you can think of as entirely owned data. You own your nodes completely, and you're the only one who touches them. Therefore, you can, without any race conditions, work on them locally. While the public state allows for stuff that you would expect from Ethereum. And if we were okay with the cost, maybe we would just bridge to Ethereum for all of this. But the reason Ethereum rollups exist in part is to batch transactions. So while Aztec aims to provide something that Ethereum doesn't have natively, which is privacy, we also are aiming to be like any other rollup, which is batching transactions and having efficiency. And therefore, it made sense to also have a public part of the Aztec network, which also lets us do things like have a very integrated user experience, or dev experience, I should say. And so the execution is by two different people. The private proofs go out, and those are fully proven by the users, while the public proofs are more of an RPC model. They're just a request for something to be done. And those are a normal sequencer model like Ethereum. Next. Go through this. Okay. So what does a private function let you do? So private functions use zk for privacy, whereas the public functions just use zk for validity. Private functions allow you to do anything like proving privately that you have received certain salary payments or up above a certain threshold without revealing anything more. Working with sensitive data, say passport data is on chain, and you want to just prove that you are a certain passport, or maybe you want to prove that you are a certain voter. You are able to hide function execution. So one unique thing is that in private smart contracts, you could actually hide the smart contract completely. There's nothing in the protocol that says that everyone actually needs the code that you're executing for you to prove that it's a valid state transition. That allows you to do interesting things, like you could have private functions that are just with a few counterparties, and no one on chain actually knows what you guys are executing. You can create proofs against historic data. Just generally, if you have a Merkle root, you can prove that you were some fact about it privately. Merkle root some hash summary of a previous block, maybe in Ethereum or Aztec itself. And when you want to move something from public to private, you use a private function. So for example, if you are privately proving that you have a certain amount of funds, you would do that in a private function, but maybe you want to use that result in a public function to then do some sort of cool action now that you've proved that your account meets some kind of criteria. Okay, next. This is an example. So this is the first example I have up of Aztec Noir. It's a very in progress domain-specific language for writing Aztec smart contracts. The Noir language it's based off of is a little more mature, about a few years of dev, like 1 to 2 years of dev, let's say, depending on how you count. And the actual language has the actual smart contract framework is measured in months. So this is kind of the first UX preview we're giving for everyone. You can fully use Aztec Sandbox. If you go into the docs, you're able to just locally get a Docker image. And with that, you're able to write smart contracts and deploy them and use this sort of syntax. So here we have a bit of what it would look like. So the analogy used here is like a card game. So you can just think of this as any protocol with its own rules, that you have some private data and you have a public component. In this case, we want to prove. This is all zk proofs. So the assert statement ends up being a constraint in a circuit that we're taking our private state, here a deck of cards or a hand of cards, and we're actually taking some value. So the value that corresponds to the highest value card. You can imagine there's numerically numbered cards, and that we're going to remove it from our storage. And what we would post is essentially the commitment to our old data, the commitment to our new data, and a zk proof that this all happened correctly, that a valid state transition was followed, but not exactly the details of what happened, and the new nullifiers, so that this action couldn't just be replayed. While the actual specifics are not able to be gleaned, if for anyone familiar with zk privacy, this is all sort of abstracted. I don't know if anyone has any questions at this point or any comments. All right. Yeah, go for it.
So where's this abstraction? For instance, the nullifiers. Can I customize my nullifiers? Can I customize what should be included and what doesn't constitute a meaningful enough change, for instance?
Yeah, so there's a variety of things you can do. So Noir itself is very generic. So Noir is just a Rust-like language that lets you do programmatic things. And when you do math, there'll be range checks. When you do asserts, they become constraints. And on top of that, we have our kernel circuits in Aztec, which are everything that Aztec needs to be confident that some valid zk state transition has happened. But everything is very generic. So the idea that there is a certain kind of nullifier scheme here is very much based on the Aztec Noir library being used here. Whereas you can go more low level, and we really aim as a roll up to provide the full functionality of zk, however you want to program that.
Thanks.
Can you elaborate about what storage is?
Yes, for sure. So storage here is sort of the idea of storage slots. There's a state tree with each contract. So based on the context, which is sort of a magic thing being injected here by this macro at the top. So this is all part of the Aztec Noir library that abstracts features from, you could think of it as being built on the raw primitives of the Aztec kernel circuit. The storage itself uses the ability for us to say, hey, there's a certain storage at a certain slot, and in this case, there would be some structure so we have storage.cards. So storage.cards would be some data structure in Aztec Noir, and we're able to map this the current account that's interacting with this contract, and some details, like say it's a card ID or maybe it's some hash, and we're able to derive a storage slot and reason about data that exists there. In the private world, this is commitments. In the public world, this might just be a hash of public data. And also, so this is private storage. And in public storage, we also have, more of an account model. And here you would be posting commitments to nodes. Yes, so the data is stored encrypted. The question is, was it stored on the blockchain? Yeah, the data is stored encrypted such that your notes, they're decryptable by your key. So you have a special key that's able to decrypt these notes. And if you are able to decrypt them, then generally you're authorized to use them. The data availability, basically the actual ability to go and find all of your data. By default, the standard way we recommend, unless you really need to find an alternate solution, is to just have everything on the Ethereum blockchain in call data or blob space, however, and have that just encrypted with the user's key, and they're able to scan that. But without decrypting the data for the sequencer, they're able to reason about it. Cool. All right. Anything else? All right. Let's go next. Thank you. And then I think for people familiar with Ethereum, the only real difference here is when would you actually combine a public function with a private function. So public functions are a lot like Ethereum. They use an account model. The state tree there can just directly store a field related, which would just be some sum. You can all the patterns, like how you would make a Uniswap pool, those are kind of similar. The specific thing to Aztec is when you're transitioning from private to public state. And that's where the fact that in one Aztec contract, you can have a private function and a public function comes in handy. So in our example of a card game, typically, we're able to prove that we discarded a card, some action that's just with my state, post that proof, everyone's happy. But typically, you at some point see other people's cards. So it's important that we have the private proof that they're showing a valid card, that they're actually following the protocol. But there is public rounds. And this analogy goes towards protocol design, where you might have private data such that you're part of a KYC set that someone has posted, okay, here's a route of everybody that has passed some know your customer check. And you're just posting, hey, I exist in this. Also, nobody else is able to claim they're me. I'm going to nullify the fact that I exist in that tree privately, and then I'm going to be able to do some action in public. Maybe it's some trading permission. Generally, we're very use case agnostic, but there's a lot of use cases where you would want to shield some confidential data and then interact with counterparties. And the card game is a very simple example of that, but generally you can think of it as like any trading use case. Maybe you need to prove some credential and then nullify it, and then no one else can use that credential, that sort of thing. Next. A public function example, here's a little mangled, sorry. So the storage, in the spirit of the language, the framework quickly evolving, the storage here is actually now kind of implied. So what we have here is a context variable that's implied by the macro, but we've gone a bit further. And as long as you have defined a storage structure in your contract space, in your contract namespace, then the storage line here is actually implied now as of like a few days ago. But in this example, we're able to get game storage that's a contract tree, a contract state tree that's just public data. And here we have this idea of storage slots again, but at this storage slot, we actually have public data, and we read from it, and we're able to read from it using Aztec data structures, an actual high-level representation. So our game object would have some start game method, and then we would be able to write it back into the state tree. And this lets us do I guess I didn't really introduce the function, but it's basically to start a game. So initialize some game structure that then people are able to interact with. And here we've just written it very simply that anyone can start any game. You just pay whatever fee on the network, and you've started a game in this game tree. Yeah, go for it.
So how abstracted away from the fields are we? And what, like, for instance, game as field?
Yeah. So this is a bit of Noir's design decisions for sure. So there's definitely some of it is the Noir language. So the Noir language is very abstract. But that being said, the native type that you will see in Noir is called field. I think one could definitely argue that you could just design the language with the native type being integer or whatever have you. You can definitely use integers, like we have U32 here. I think it varies. I think the biggest abstraction leak you'll see is that you see fields. And there is the argument made that because fields have certain properties and we want to use them for efficiency because, well, all of our logic in zk operates on fields, and operating on them natively gives us efficiency advantages, that it makes sense to leak the abstraction. But yeah, I would argue that practically you could just have everything as an integer. You can make high-level structures. Clearly, you have a start game data structure there that's quite high level. But the Noir language, I think definitely you'll see some things leak through. But I think the biggest one is just the use of field as the primary integer type.
So do you need, as a developer, to be conscious of, for instance, the degrees?
No, that's definitely that I'd say is something that I would really just leave it there as like you need to be comfortable using the word field, and you have to maybe know that there's some different edge case logic with fields, but generally you're going to be able to just treat these as integers, especially for typical blockchain use cases. You're not going to have to worry about anything like a degree or anything like that.
Is the degree fixed or dynamic of the circuits?
It's fixed. So yeah, we have parameters that are chosen. So Noir itself is flexible, but our design parameters have a fixed degree. Any other questions? Cool. Move on. So yeah, I've already kind of talked about this. You basically can use them together. You have a commit reveal scheme. That's the core idea behind using public and private together. You can definitely do things entirely in private. The main thing you could do entirely in private is send assets. So assets can be represented as notes, and those can be entirely, you just encrypt a note for someone. You have sent them assets. There's a message they get on chain that they have received a note. But for anything with counterparties, so you could kind of argue that sending money is something with a counterparty, but really it's pretty unilateral. They can't reject your money, so it's a unilateral choice of yours. So everything unilateral, just you deciding something, can be done in private. But when you have counterparties, then you have to move to public, and that's where the ability for us to call public functions from private is important. And we aim to provide a seamless experience, something that isn't really available in other networks. Next. So you in the same vein as public to private, we have L1 to L2. So it's almost the same abstraction idea. So we have, for both of them, we have these message boxes, and you're able to connect quite different designs with each other. And in the same way, we're able to call, say, the Bored Ape contract and connect to the Ethereum network. Next. All right. So I've touched on this a bit, but essentially they have different execution environments. The real execution environment we're thinking for private functions is someone's phone that we're aiming, say, a few minutes. There is there's a bit of computational load doing the zk proofs if you're going to do it on consumer hardware. And then the public sequencers we're assuming are going to have better hardware, probably some node with lots of cores you'd want for such a thing. And those sequencers are able to do public functions in a way that's they just see the inputs And then they do a zk proof, but it's a zk proof, obviously, without privacy. It's just for validity and succinctness to post on Ethereum blockchain. Oh, yeah, go for it.
So the sequencer performs both tasks, the proof generation and packing those and sequencing those into an L2 block?
Yes, yeah. So the sequencer has the job of, so the user has the job of sending already proven private state transitions and public requests. You can kind of think of it as an RPC request, similar to Ethereum. But the sequencer then needs to take both the private and the public and roll them up. So it's going to first take the private functions and validate them, which is quite cheap in the zk world. And then it's going to sequence the public functions after the private ones, which has some idiosyncrasies. It means that you can, in one block, in one rollup, you can have a private to public call, but not the other way around. But the sequencer is in charge of actually making one zk proof in the end, and that's going to be posted on Ethereum. Yeah.
So I'm not quite sure that does this sequencer actually recursively verify the proofs that devices generated or not?
Yeah, so there's layers of rollup. There's definitely recursive proof generation going on. So the zk proof is posted in one format that's a little bigger but easier for the private to execute on consumer devices. So the proof size is a bit bigger, but it takes longer to explain in the level of detail I understand. And the public sequencer then is able to take it and take all of those inputs, recursively roll them up, and then we take different design parameters for when the public sequencer actually posts on Ethereum, such that the data is as small as possible. So this is just assuming you're actually going to want to build on the sandbox, although I'm not going to go too detailed here. The docs are really what you'd want to reference. But in public state, we kind of have a simpler view of the world because there's less design considerations in the public world. Generally, you just have storage slots, and at those storage slots, you can put structures, any kind of structure. You can have an address to account balance map, whereas in private state, we have sort of optimizations based on, do you have a singleton updatable note? But if you have a singleton note, you have to be sure that it's really only one person working on it, because you can't have assets as a singleton note, for example, because you can't unilaterally give someone money with a singleton note. That would imply actually that you'd have to nullify their note, and that they would have to realize you nullified their note. And that's just generally not something that can be, that's just generally something that introduces race conditions. So for an asset, you would have to do a collection of notes. And with that, you're able to just insert a encrypted note into someone else's set, as you can consider it. And they're able to discover through on-chain messaging that they've received an encrypted note, and through their key, they're able to decrypt the note, and they're able to use that. In the same manner, you can kind of think about this. So what if they didn't realize they got the note? Well, this kind of leads to the idea that you can never prove someone has withheld a certain amount of money on Aztec. So for example, say I just simply did not realize someone has sent me a note and I'm trying to prove my balance. Well, I might not prove my entire balance. And that's just generally true of the execution model, that you can prove a balance is greater than or equal to a certain amount. However, to prove that all the notes have been discovered by the user is not something that's generally possible. But obviously we provide mechanisms for users, and users proactively do want to find their money and be able to use it, obviously. Next slide. Oh, sorry, go on.
So do I get it right that every set needs to have an owner, and using asymmetric encryption and use their public key to
encrypt
notes for them?
The fact that the public private distinction is important. Yeah, you with their public key are able to encrypt it for them, and they're able to decrypt it with their private key. Yeah.
So there is no set for, let's say, group of users, or
Yeah, so that's exactly where we wanted to have the simplest design possible. So one thing would be to only do private state. However, there's simply use cases that are just not feasible unless you were going to do like a very complicated scheme like homomorphic encryption. But with just using asymmetric encryption, having shared state in private world is not really something you could do. To have that, you need to have the kind of the same model as Ethereum, have pooled assets. And for that, you could at least work private to public. So you can just reveal when you're actually pooling assets. But the idea of shared notes, not really. You can have a multi-sig account abstraction that owns notes, but that's a bit different, obviously. All right. Any other questions? Next. Okay, so this is getting in the nitty gritty of storage slots. I'll probably, in the interest of time, not go too much here, but essentially it's a bit what I've covered already. So every account contract has a storage structure, and that storage structure defines a mapping of storage slots to data. And based on those storage slots, which are unique for the contract and the user, you are able to put data in a way that the Aztec rollup contract understands. And it's probably, unless someone has any questions, it's probably the detail I'll go into here. It's just the way we build our storage abstractions. Yeah, go for it.
When blobs, do you support EIP 4844 yet?
We do not currently, okay. I mean, we're definitely working with the design space of blobs. I don't think I have the best answer for that, but we're definitely looking to use them.
So right now the default is like always using cold data?
Yeah. Right now we've built everything with whole data. We're still, like, I would say about 6 months into designing Aztec 3. So yeah, that's definitely something on our roadmap, but currently everything's cold data.
And how about non-Ethereum data availability solutions?
Yeah, so that's really up to, so there's nothing in the core protocol that are saying that you are going to post the full data that you are working with. Everything works as long as you are approving state transitions between commitments. So that's just hashes of data. You can not have the data. Now, if you don't post your own data on chain, or if you're using a contract realistically that doesn't post your data on chain, then you might struggle to find it later. So it's definitely the safest thing to post everything on some data availability layer native to Ethereum. That being said, if you want to use alternate data availability, I think that is a big area of development. That's if you're going to post a lot of data, you can definitely take advantage of the fact that you don't need to, in the protocol, post it all on chain. You can use something like EigenLayer, for example. It's definitely open design space. Okay, so just a bit about account abstraction. There's no externally owned accounts on Ethereum. This is kind of informed by how hard it has been to move to account abstraction on Ethereum. We want to kind of, from the get-go, not have this distinction between contracts and accounts, just kind of encourage everyone to consider, okay, one of my first choices is what account am I actually going to use? So you might have something very Ethereum-like based on signatures and just owning a single key. But you might have something more, you might have a native multi-sig, you might have something like Touch ID, something more Web2 focused, some mix of MPC. There's really an open design space here. It also just removes how much we're encoding in the protocol. So there's just, the protocol itself just considers that there's some private function entry point, but doesn't assume too much about it. Then the private function entry point itself encodes what in other places would be encoded in the protocol. And this lets us not enshrine signature schemes, gives us some future proofing as well. Next, unless there's questions. All right, so I can flip through this. So this is kind of given that we have native account abstraction. So you have some decentralized application, and you're calling some function on it. The first thing that is done is you then whatever authorization mechanism your entry point is assuming. So let's say we're just signing our payload. Then we execute the private account entry point, and that in this case, it would actually exist on your phone, for example, or your local device. And then what you're actually posting is you're posting a zk proof that you have met the criteria of your account contract to do the action you're trying to do. And then you're able to finally call the other contract that you're aiming to call, but the entry points of every transaction is your account, your private account contract. Sorry. All right. Any questions there?
I guess assigning payload is optional depending on what the account abstraction is doing exactly.
Yeah, exactly. So you might have multiple signers. You might be signing with your Touch ID signature. But there's definitely a whole bunch of design space there. You can have just pokeable contracts. You have a contract that anyone can call, and you have some alternate way. Maybe some paymasters deciding which ones actually go through. There's definitely various things you could do. Ooh, next. Okay, so we're just going to go through a very simple ECDSA wallet. So in client side, all of our tooling right now is in TypeScript. So in TypeScript, you would sign your message with your account contracts library. So there'd be some utility. Everything we're considering is kind of, okay, stuff people can do in browser. We're assuming the crypto space is very weary of downloading random applications for good reasons. So we kind of want to be like, as much as we can run in the browser, which is a sandbox, conveniently, something that shields users a bit from malicious code. And so they are a little more comfortable downloading random code. So we have some TypeScript here, and this is example of how we do it. Again, it's kind of mangled here, unfortunately, but we would just, I guess it's really just simply, there is some utility library that lets you interact with your account contract. Next. And then there is some noir, that is the entry point that's determining the validity of your transaction. So is this transaction actually able to be done by this account? And this is a zk proof. So this is all private function execution. So the details here, you might have data that you're operating on, but you're operating on it just on your device. And what you're posting on chain, again, is just a zk proof. And we strike a bit of a balance. It's not the smallest zk proof. It's one that strikes a balance between size and being fast to execute on consumer hardware. Next. Okay. So a little bit about L1 to L2 messaging. So L1 here, just simply Ethereum. This is conceptually pretty similar to the public and private messaging. Both of them use message boxes. This idea that they're pretty separate execution environments, but they have some built-in way of actually at least consuming messages from one another. In Aztec Connect, which was the previous product of Aztec, we use this a lot. This concept conceptually, we had it less flexible, but we built it. We had abstractions you could build with contracts that let you do things like batch trades for Uniswap. And this is the kind of thing where, other than this being the mechanism for defining assets at all, because there are no native assets on Aztec, we are also thinking there's going to be cool roll-up adjacent things like batching trades on Uniswap, or generally batching things to get efficiency gains while keeping some privacy. You just are showing that you're hopping on this bus that's going to call the contract, and then the contract will consume the message from the L2 and post one back, and then that message can be consumed with a private function. Next. Or sorry, is there any questions or comments on L1 to L2 messaging? Okay. So we're going to go through the transaction life cycle, just kind of holistically. Next. Okay, so the user is going to connect their wallet to some app. There's going to be some workflow to prove the account interaction. That's then broadcast to the network. Once the account has proven that the user's intent is valid, the transfer function is actually called. The transaction is put into a rollup by the sequencer, and the block is settled on Ethereum.
I have questions. Why would wallet or app need to know anything about kernel proof? Or is that unrelated to kernel circuits?
That's a good question. So I didn't make this slide, but okay. So prove account interaction. So right. So when you're doing private proofs, you do have some idea of the kernel stack. So you're doing part of the layer of the kernel proof. So there is the idea of private call semantics. So you might prove a private call stack. You might call multiple private functions with each other. And you are actually doing this entirely in your wallet, as we call it. So your private execution environment. And that becomes part of, you can kind of think of it as an inner kernel proof that then is recursively defined with the outer public proofs. But yeah, unlike Ethereum, you do have quite a bit of machinery in your private execution environment, which we're calling a wallet, but I think we're now calling a private execution environment. And basically, yeah. So the reason I think kernels in quotes is just that you are doing kernel-like things. You are proving recursively a private function call stack, such that all those details are proven by you because they can't be proven by the sequencer without your data. And then you're finally broadcasting that to the network. But yeah, there is then more layers of what you would call a kernel proof.
So that makes sense, but still doesn't answer the question, why does the app need to kind of touch the kernel proof?
Right.
Why not just broadcast, once we have a kernel proof, why not just broadcast it to the sequencer?
Right. Yeah, that's a good question. I think I'm not clear on the slide the most. Yeah, I'll try to get an answer for you later, but
maybe for UX. Yeah.
Wallet doesn't have the user's credentials, maybe? I mean, user's wallet is connected only to app. I mean, users private stuff. You know what I mean? The connect wallet stuff at the beginning. So this whole wallet is only targeted for the proofs and verifications of the patches and everything.
Yeah. I'm not sure it's the most important detail. Yeah. All right, next. Okay. So next we'll talk a bit more about Aztec Noir, which is the smart contract framework built on top of Noir, which is a domain-specific language that we're building that's very Rust-like. Next. That's basically what I just said here. So Noir, it aims to, I think there's a big distinction we draw from other languages. So there are languages in the ZK space. There's Cairo, which is also Rust-like, but doesn't have privacy. There's CIRCOM, which is very popular, is used for ZK proofs, has privacy, but the abstraction is something maybe a hardware engineer would appreciate. It's very wires, circuits. It's not usually the way programmers think, although I think it's a fine abstraction if you are fine with that kind of level of detail. But what we aim to do is to make things more natural, to really make the developer experience as natural as possible, and to allow abstractions that don't deal with circuits. So with NAR is able to unroll a lot of logic, for example, and see what really happens with functions and simplify them down into optimized circuits without you having to think of circuits, which can be more efficient, because if you are always thinking in circuits, then you're always encoding that there are certain constraints, whereas Noir is able to reason about which constraints are actually needed. So not with high-level languages, we can have better DevX, but we can also have optimization opportunities. It's not to say that you can't have optimization opportunities at low-level language, but the utilities you make that then need to expose those, and sort of the DevX of the libraries in Circom then to actually be optimized is a bit worse. Right. Next. Okay, so yeah, this is kind of a laundry list of everything we are considering currently in Aztec Noir, which is really kind of a bit of a framework, a bit of a toolkit on top of Noir. This is definitely something we're going to consider in the future, whether it makes sense to consider something more of a core of Aztec Noir, maybe consider part of it an Aztec STD library. But currently, a lot of this stuff is stuff we consider we don't really want to give users the DevX without it, because a lot of this stuff are primitives that the users have to do to really do anything useful. So we have the ability to call public to private, the ability to call Ethereum, the ability to nullify notes, just deal with storage abstractions, not have to worry about the nitty gritty of our kernel circuits, which talk in commitments and nullifiers and all that stuff. And we have event emitting, so being able to emit both encrypted and plain text logs, which show up in Ethereum call data, and for example, how someone would realize that they've actually received a note. And we have safe math tooling, which is just building on top of the building assumptions that may not be in core Noir just for safety. And this is going to expand over time. We're definitely going to also grow into more of a base standard library and alternate standard library approach as we go forward. But currently, Aztec Noir is the sort of layer on top of Noir that it makes all this kind of sane to work with. Next. And what are we targeting? So basically, why are we building Aztec Network? I think for me, the core of all of this is that privacy is a best practice, in my opinion, that it comes with its own challenges, but the idea that you have, there's a spectrum of complete on-chain public and you have total privacy. And I think there's a lot of best practices in between. The idea that everything a user would do would connect them. They pay for a coffee and then, you realize that they bought an NFT that went to zero. That kind of stuff's doesn't feel that great. So we definitely think that privacy primitives are best practice. And very specifically, you might do stuff like in consumer finance, you might have someone post data about your financials. Okay, so they're a trusted party posting about your income, or maybe your income's on chain. And then you're able to use a ZK proof. So you don't have to then go to that trusted party and be like, okay, can you please sign this message saying that I have a certain amount of income? You then own that data and you can just prove with a ZK proof trustlessly that you meet certain criteria. On-chain auditing, for example. Hidden information gains. This is kind of the example given, but to the extent it makes sense to do these kind of things on-chain, you definitely have to think of efficiency, but you can definitely have a game like poker done with ZK proofs, although a bit complicated. You can do decentralized ID solutions, and the example one might do is a passport. Passports do use cryptography inside, so in theory, you could have an account abstraction just based off scanning a passport, and you could do stuff like Touch ID. You probably want to combine these with other things, but that's kind of, the more you layer these solutions, the more you kind of get somewhere where you can robustly prove things in a way that's not just people owning public keys. And you could prove identity this way and in a private manner, such that you can prove that I'm not anyone that has done something before, but I'm not going to show you who I am. Payments. So this is people definitely want day-to-day finance to be private. I think that goes without saying. People don't just post their bank account details every time they do a transaction. Doing private voting and some idea of supply chain. If you have some party posting data, you can prove provenance that way. Anything here? I think it's kind of self-explanatory. Mostly things you would want to build on blockchain, but we would aim to make privacy technically feasible and let app developers focus on their core logic. Next. All right, so the rest here is sort of just a bit more detail about public and private state. Next. Okay, so again, we have user devices. We're doing quite a bit of cryptography research aimed at having things runnable on user devices. So there's stuff like Goblin Plonk that our CEO is coming up with, and lots of stuff that I'm hoping to understand more, but still have not soaked in my time here. But all of this, a lot of our engineering is going towards this idea of running private transactions on a user's phone in a reasonable amount of time, which would be a few minutes, we would say. And then with the public space, we're a bit less worried about efficiency. We're assuming greater hardware. We're assuming that the people running sequencers in the network are able to kind of sit more of like a server with more cores, and they're able to parallelize a lot of this processing. And therefore, we're definitely focused on having an efficient public zkVM, but that's sort of what we consider the less hard engineering challenge. And of course, then it all goes to Ethereum, which is definitely kind of the point for us to extend Ethereum with privacy, the goals of a normal rollup, efficiency, all that. Next. And to just iterate. So what's a public state? So public state is just the account model. Then the account model is what Ethereum basically uses. If you have Alice, you would look up Alice in a state tree and you would get her balance, and that would just be a number. Next. While for private state, you have a commitment. So there's an owner. However, this is posted encrypted, and the actual data is just known by the person who has it. So in a similar way, this is kind of the same thing, but you actually have multiple of these values, and every time you get money, you would just have a new note at a different slot, and you accumulate these, and these represent your total assets, and then you're able to prove some subset of them are above a certain amount, and this is all sort of how Zcash or other most zk private cryptos work this way, that you're then able to prove that your amount is greater than a certain amount or equal. And that lets you then, by the rules of the contract, do things like claim that money publicly or in Ethereum. Any comments? No. Let's move on. All right, that's fine. That is to say, public, we have an account model. Public, we have private, we have a UTXO model. The UTXO model just very simply being you have lots of little pieces of data that are encrypted. Or, well, in this case, encrypted. Next. Okay, so there's some. So let's say we think of our private state tree as these closed envelopes that are only opened. You only open them to yourself. Nobody else sees what's inside, and then you're able to just add them to another. You're able to just basically take that. In this case, we're going to take 5 out of it, and this requires us to actually nullify the existing envelope. So in this case, I mean, the analogy gets weird, but the envelope continues to exist, closed, but no one is ever able to use it again. It exists in the nullifier tree, and what you do when you're trying to use private state is you prove that it does not yet exist in the nullifier tree. This was probably, if you're familiar with private cryptos, it's probably not that shocking to you. But this is the main this is the main paradigm to be able to privately represent assets. Next. So every we have a distinction with the private and public functions. So the private functions compile to circuits. We have a intermediate representation called ACER, which is what Noir uses. And this has all of this fun stuff, like there's a proving key and a verification key associated. And We have a bunch of inputs to our kernel circuits that are all needed to verify these proofs are valid. Whereas with public functions, actually, it's quite a different model. It's still using zk, but it's a zkVM. And it's there's a subtle reason for that, which is that a sequencer that's doing public execution, they actually need to get paid for work that doesn't work out. Say some slippage parameter exists and a certain price has moved, which means that the transaction reverts, but you still want to prove as a sequencer that you did work and that you're going to get paid for it. And if we were to do everything with our circuit model, there gets a point where a user could just erroneously cause a sequencer could erroneously cause the proof to just not work. So they would just post witnesses that make no sense, and then they would take your money. And conversely, if you can't distinguish between the two, if you always decide in the favor of the user, then the user could grief the sequencer. So there is a circuit model for private functions, but for public functions, we do a zkVM where we just prove one instruction after another, and that all the proofs are kind of recursively instruction by instruction. Yep.
And so given that the degree is fixed, how do you deal with the situation where the zk circuit is unable to accommodate for some very complex transaction or very complex message, for instance, one stemming from Ethereum? Like, how do you prove that you couldn't prove a given piece of data payload?
Okay, well, I think I know a little bit less about your first question, not having that much of a cryptography background. But for your second question of how do you prove that something that you were not able to make a valid proof, that's something that's not in the design. That's not really something you do, in the sense that you're always posting a valid proof. So if you are in a private world and you don't post a valid proof, well, you're just doing nothing. That's on you. You're just sending some data that's going nowhere. And that's something we're hoping that the sequencers are able to validate quickly enough that it's like, okay, yeah, well, you're going to get throttled and that's it. You're wasting your own time in essence. Whereas in the public world, you're always posting a valid proof. And again, you're just wasting your own time if you don't. You're just missing your block. You're always posting a valid proof that a certain sequence of instructions has happened. And that certain sequence of instructions, so if you think of our assert in var, if that assert is in public world, you're actually going to have the sequencer proving instruction by instruction that we got to the assert, and that the value of the assert is, false, and then therefore we're going to revert, but the user still has to pay a fee. Whereas in the private world, the user would realize the proof's not working, and they better know, there's no point posting it, or otherwise you're just going to be seen as spam.
So there's no censorship resistance in the sequencer layer? Or I wonder, how can a sequencer defend themselves against the accusation of having censored someone?
So in the sense that, well, they need to post a valid proof that they have ran their public function. They need to prove that they ran it instruction by instruction, got to a valid result. So I guess, what do you mean by censorship here?
So the public functions are run in a VM?
Yeah. There's two models. So this is only for private. There's a circuit abstraction, but there's actually a public VM. There's a zkVM for public functions, which is done instruction by instruction. And as a public sequencer, you need to prove that you've actually done the right sequence of instructions.
Okay, so this would be a problem for private functions only, and those we assume are provable anyway because the end user created the proof.
Yeah, exactly. There's less concerns if you are doing your own private computation. I mean, you're not like paying yourself gas or anything. Even you're just posting the final result, and you can waste your own time if you want to.
And then the gas limit per block is chosen such that no Aztec block can be crafted such that it be impossible to create a proof for said block.
Right. Yeah. So I mean, eventually, if you run enough instructions, you would hit some gas limit, and then that would be part of the public kernel circuit.
Gotcha.
Cool. Anything else? Any other follow-up questions? All right. Next. And this is just some final details of how this all looks. Squishy. This was kind of an early slide. It's not called a squisher, but there's sort of layers of private proofs and private transaction proofs and public transaction proofs that are put to base rollups, which are then merged together. And finally, in the final layer, we have a we've recursively done all this, and then we posted the Ethereum smart contract. I'm not sure how helpful the slide is in hindsight. It was quite early. Next.
What does the squisher do?
Yeah, I'm realizing as I look at this was quite an early slide. I'm not sure it actually. I'm not sure you could, because there's an ordering possibly required here with all the public proofs. I'm not sure you could just.
So you mentioned that the user generated proofs were big to save on computation. So probably there's some compression going on.
There's definitely some compression going on. So there is two layers. But the specifics here, I'm not sure. This was also kind of an early slide. I'm sure some details have changed. Next. And this is just getting to the end, but the kind of workflow you're able to do. So you might have this is getting into one concept that's portal contracts. This is also where I get confused because it's an old slide. Okay, I'm gonna ignore the slide a bit, but basically you always do private to public first, and the reason for that being that the private functions do not affect the execution of the public functions, but the public functions might need the outputs of the private functions, whereas it's not useful to do the reverse, because if you do the public functions first, well, there's no way actually for the private functions to have that be useful, because when you're proving things, you can only prove things about state transitions, and you can't really know what's going to happen in the future. So the public functions are all kind of shared state. So what actually ends up happening, like what is the state of a Uniswap pool after a bunch of public state transitions? That really depends. So the only useful ordering, because it's kind of race condition free, is to do all of the private calls first, and then the public calls in the same rollup block are able to consume private messages. But if you were to do a call back to private, it sort of has to go into a message box, and then you're able to consume it in a private function later. And I guess this example was originally talking about L2 contract deployment, but I don't have much to say there. But I will say every L2 contract is able to have a portal contract, and that's just basically a nice way of saying this connects to a certain Ethereum contract, and there's nice primitives for having the Ethereum contract. If it's sending a message to the contract that's a portal of, it's able to affect things in the L2 portal and just send L1 to L2 messages that way. Oh, yeah.
Okay. So communication with L1 is always public, but can be initiated by private.
Yeah. You can consume notes from the L1 in private world. And you can post them to the L1, but the actual notes would then obviously be broadcast. But you can prove state transitions, you can nullify all that kind of stuff in private world.
Okay, and when it comes to race conditions and private transactions, you always just have to assume there will be none, right?
Yeah.
So I can do a bunch of things to my state, but if someone insert a node into my set before I
right. So
is that problematic?
No. So in private state, you're able to do proofs. So you're always picking a state tree that you're going to prove with. And there's always this check that's there's validity to what you're doing, that you don't have, you're not using any nullifiers that don't exist, or you are using those that have been since nullified. You can definitely have race conditions within yourself. Like say if you just post two different private transactions trying to nullify the same note, the kernel circuit is designed to realize that even though you're saying, okay, there's this old tree that doesn't have my nullifier, I'm proving against it, and there's this other transactions also old tree trying to use the same nullifier, then it's able to validate those kind of race conditions. But in terms of if someone just inserts a note in your set, it doesn't really matter in the sense that a note that you don't know about effectively doesn't exist. You're always making proofs about specific notes. So if you're proving you have $10, you're doing a proof about very specific notes, you're nullifying those, and you're making new notes. But yeah, though anything that if you just have extra notes, that doesn't really cause a race condition.
And I cannot nullify someone else's notes.
Right. Yeah. You would. Yeah. Not unless you were effectively able to spend them as well. Yeah.
Right. And then when the message comes back from the L1, what are the constraints then?
The message comes.
Can it create a node for me? Can I add something to my set?
Right. So what you would do is you would consume the L1 note, you would nullify it, and then you would have a private smart contract that's connecting to the L1. So you'd have what we call a portal contract. So you'd have the L2 designating an L1 contract as the portal. That L1 then sends a message to the L2 contract. The L2 contract has a private function that says, okay, I'm going to take an Ethereum message, I'm going to nullify it, and I'm going to make a message on Aztec. And then that can be an asset. That can be, basically, that would be one way to define an asset, is the fact that you've gotten a you got a message from an Ethereum contract that's, say, wrapping USDC or Ethereum itself, and then you are consuming that in Aztec privately by nullifying it. And then in Aztec, you are then minting a note, which you can do just because you're proving, you've done a valid state transition. That's whatever the contract says you can do. And then you're able to then privately make yourself a note.
So then it needs to be, on Aztec, I need to kind of make a transaction to consume a node.
Yeah, exactly. Yeah. You can't just kick off. Well, you have to appreciate, the fact that, it's just happening on a private user's device. There's nothing that could be like, okay, this user is going to now be doing this proof on their phone for 2 minutes. Then, that kind of has to be a pull model, not a push model.
So I can do a round trip in 2 transactions, right? I can send a transaction, private transaction to a portal, goes to the L1, something happens on L1 sends back. That's all kind of...
Yeah, exactly.
That happened, that was all triggered with one transaction on Aztec. But then the result, when it's delivered back to Aztec, I need to consume it.
Yeah, anytime that something...
If I want the state to be private.
Yeah, exactly. Anytime that there's a sequence of events where something is now private, and you're transitioning to private, that is now something that it has to end there as far as the sequencer is concerned. The user will then need to do their execution on their device and then, post in the next roll-up block, and then things can continue.
Awesome. Thank you.
Anything else? All right. So I think this is getting to the end of the talk. Next. Okay. Well, yeah. I'll take any general questions about anything, really.
When we deploy a smart contract to Aztec with some private functions, where those circuits are stored? On a user wallet or on a blockchain, on both? Yeah,
so generally our default, when it's basically the question of data availability, we don't need actually the code to be published on the blockchain, in the sense that as long as users have the code, they're able to do the private execution. It doesn't actually need to be known by the sequencer at all. And in fact, that there are patterns you could do like that, where you and some counterparties know some private contract, but you don't really want anyone to even know what you're doing. You want privacy, even to the point where, this contract's completely hidden. But our general default data availability idea is you just post on the blockchain. Therefore, everyone can find this function and execute it, because otherwise it's not a very useful contract if you can't easily get the code. But definitely there's different things. I think the strongest thing to do is to post on a blockchain, but it's also relatively expensive, and you could consider alternate data availability solutions for sure.
But you mean code? The verifier needs always to be on the blockchain, right? For the code.
There's a generic verifier. There's a single kind of Planck verifier, as it's called, that does that. The final proof is just a standard Planck proof, which is the small kind of proof I was alluding to, and that is able to verify any circuit. And then each private function doesn't need their own verifier. You can just have a hash of the bytecode in essence. So we have this ACER representation, abstract circuit intermediate representation, and you can just post a hash of that, and that's enough to verify. Now, the public functions definitely have to be on-chain because those are ran by the sequencer, and you actually want to prove those instruction by instruction.
Any more questions?
I'll take even very general questions, anything but Aztec as well.
Kind of all-in-one package. You know, you have sequencers. You have you support rollups.
Right. So I mean, we are a rollup. So we're aiming to be a very general rollup, but we are a rollup on Ethereum. They could put rollups on Aztec, but the gains are probably not going to be as much as when you're posting on Ethereum. Definitely the closest thing to rollups we're considering on Aztec is just alternate datability solutions. People can, you definitely can do similar stuff like that, but I think the biggest, I guess maybe clarify the question. What do you mean all-in-one package?
You know, it's general. I don't know what's the idea behind Aztec.
Yeah.
After all, you know, if we don't have Aztec, we could do all of these.
Well, so I think the main motivation behind making Aztec is that on Ethereum, actually, you can't really do privacy. You can definitely do individual smart contracts that have privacy. You can have contracts that use zk, but this is meant to, well, A, be roll up, so batch transactions bring efficiency to Ethereum, and B, to provide privacy as a primitive. So when you are doing things in our roll up, not only are they more efficient than Ethereum, but we actually have an environment that from the ground up is made to do privacy and zk. And while that you can do CIRCOM on Ethereum, it's quite costly, and it's also it's the programming model of Ethereum is not very friendly for privacy. You have to build a lot of primitives just to be able to do things. And at that point, but this is kind of if you tug on that thread, we think you get to Aztec.
If I may elaborate on that, Noir, you can compile Noir to be verified on Ethereum too, right? So it's very modular. So you have Noir that is just a language with different backends. I believe there is a Plonk and Growth 16. And
it's like Halo
more,
2. There's a bunch of random black.
I think there is other plan to be developed, and there is a Aztec rollup which comes with Aztec.nr.
Basically,
and which is a framework that kind of allows you to use Noir specifically on Aztec.
Yeah, like the Plonk verifier that is used by the Aztec rollup in general just can be used on Ethereum. Like you can just prove zk using that on Ethereum. So it's definitely why all of this design is just to make the developer experience as good as possible. And I mean, definitely in broad strokes, you can do everything on Ethereum, but there's a reason rollups exist is mainly that Ethereum doesn't support the throughput needed for everything. And also we think that we have an opportunity to reconsider the DevX and actually make an environment where all of this is quite nice and there's a lot of interoperability.
On mainnet, or it's just
Aztec is not currently active on mainnet. No. So this basically, the model of the sandbox is you would have an Ethereum running locally. So just Anvil. You have you can fork Ethereum state, do everything. You can have your smart contracts locally on your Ethereum instance. And then we have local packages that are the Aztec Sandbox, and that's able to do everything in such that it's connecting to an EVM instance, but it's just on your device. So we're not at testnet stage yet, so we're definitely not at mainnet stage yet, but we do have the whole end-to-end EVM compatibility, or rather building on top of the EVM, but it's all just currently on one developer's machine. And the idea is we're collecting feedback, trying to get people in the hands of people. This was like about a 6-month effort to get the sandbox out. And at this stage, we really just wanted to collect feedback and see how people feel with the UX or the developer experience.
I think it's worth mentioning that Aztec is the first, well, soon to be the first L2 with privacy features, right? We have some L1s like Mina or Alio or Zcash before. Alio and Mina allow to do general computations. They are still in the very early stages. They're just opening their testnets. I believe it's still Alio is still testnet. Mina is kind of in superposition. They have some stuff on mainnet and some in testnet. But they're separate blockchains, so it's hard to move liquidity between them. So I think it's the big thing about Aztec launching Sandbox is like, okay, we finally have general computations, privacy on Ethereum, reasonably priced on Ethereum. Like, it's just so difficult to do an zk on Ethereum. So the promise of Aztec to make it,
Yeah, and I mean the hard problems we're trying to solve don't end there. We're trying to be basically the first L2 also that has decentralized sequencing, decentralized upgrades. There's quite an ambition there, and I think a lot of this stuff would be breaking ground.
Questions? Orest?
Oh yeah, I just remembered. I wanted to follow up on that. What did you mean by there was something about governance and how Aztec combines L1 and the L2 governance? How exactly? What do you mean by decentralized upgradability? I assume it's connected.
So I'm not sure what you're referring to what I'm saying, but decentralized upgradability is just the idea that the rollup contract needs to have an upgrade, and it would be great if every time Ethereum upgrades, we're like, oh, hey, slip in this Aztec upgrade and just have everyone verify it and piggyback, but it doesn't quite work like that. So we need our own kind of consensus mechanism to actually say that Aztec is going to have an upgrade, and there's actually RFP for upgrade proposals right now. But going back to what you were saying with L1 to L2 combining, I'm not entirely sure. I think what I was referring to is the idea that you can provide features. Say you have a whole bunch of people who want to trade on Uniswap. You don't have to have them all individually call to Uniswap. You can actually batch their trades and then just kind of have a bus of trades and then kind of distribute on L2 the result.
Oh, okay. No, I meant I was wondering about the decentralization. And do you have thoughts? Do you have more insight into how Aztec intends to decentralize the upgradability and also the sequencing process? Yeah.
So there's Fernet as our current. We have a spec for decentralized sequencing called Fernet, and it's the details. I'm definitely not the best to talk about. I can talk a bit more about the decentralized upgrading actually, but Fernet is basically there's some sort of staking model and users and people pre-commit to blocks, and then you get slots, and then there's a prover network, but definitely very high level on that one. The upgrade part I'm a little more in depth on. The idea is to have a model that's similar to Ethereum. The current idea is that we would start with something very, try and keep things safe at first, which is to say that the rollup would be immutable. So the rollup contract would not change. What we would instead do is there's going to be basically a canonical, there's going to be something pointing, hey, this is what we think as the canonical Aztec, and what we'll decide that is actually staking. So there's going to be a token that's staked to control the Aztec network. But the first part of that is simply that people are just kind of continuously voting on what is the current Aztec. And at first, the rollup would be entirely immutable. So one thing you would have is, so we don't define the assets on Aztec. So it would be sort of up to the portals, as it were, to decide what is the Aztec that they deal with. Do they actually, you can have a variety of designs there. You can have a design that accepts whatever the stakers are saying is the current Aztec. You might have a design that is sovereign. People are just like, okay, I really rather not have to, I really rather upgrade by actually just withdrawing my funds, going to a completely different rollup. And then we're thinking eventually, though, to move this to a model that is probably the better user experience, which is that mostly the rollup we would just expect everyone to upgrade to new rollup, and we'd fork the state of the old rollup. So the real distinction being that in the first model, we would start fresh every time. We'd have a new Aztec that has no notes in it, and then people would redeploy their contracts. Whereas in the other model, we're kind of assuming that everyone's gonna follow the staked Aztec. This is, take with a grain of salt. This is still something in RFP, and I definitely think that it's a complex topic. So if you could poke holes on it, I mean, I would be surprised. But this is currently RFP, so we're definitely open to any thoughts here.
How is that? How are those two suggestions compatible with not issuing native tokens? Like if all tokens are locked,
right, so there would be an Aztec token on L1.
But if all other tokens are locked in the immutable rollup, would they be locked in the rollup contract, or would there be a separate immutable bridge contract? Right.
So the rollup contract is just a message passing contract, and it is it would be governance-less. It would just be like Uniswap is, where people there's just new versions of it, and it continues to work completely as it were. Now there's a few things there. I mean, it's kind of a complex topic for sure. Like there's liveness of the rollup contract. It actually needs sequencers to continue to use it. So it's, even if it continues to exist, I mean, it doesn't meaningfully exist if the sequencers have abandoned it. But say that there are sequencers still on the old Aztec, then it would just continue to work as it were. Then, okay, so you have this immutable core message passing bus, but then all the portals are designed they're just however you want to program them. So you can have any governance model then. You can have just a multi-sig portal with training wheels, and it's up to the user's comfort then if they're comfortable using that. Or you can have one that just immediately upgrades whenever, just moves assets whenever you see that Aztec has moved stake to a new staking environment. There's definitely, I think, I don't have all the answers here. Definitely a complex topic, but there's currently ongoing work on this, I would say.
Cool. Any more questions?
Okay. The last question, like Aztec can be seen as a tornado cache. So do you don't afraid of like sanctions?
Well, I mean, there's Aztec is a message passing bus on Ethereum that is not tornado cache.
Yeah, but so like that is usage is like, okay, I will have rollups. I can transfer like privately funds between accounts. Like it's perfect mixer.
Sure. No, and yeah, I'm not trying to say that it's not a real question, but it's just we definitely have a distinction that we're drawing, that we're trying to solve the technical problem of privacy. Now, the compliance problem of privacy, I think that's completely different. That's definitely not what this talks about. But I don't think anyone would say that's impossible to make compliant private tokens. That is just something that I think is going to affect the ecosystem building on Aztec more than it affects Aztec itself. But definitely the distinction we draw is that we're solving the technical problem of privacy. We're building the building blocks. Now, if Coinbase has to come in and KYC everyone doing privacy, that's another topic, and definitely one that I'm not qualified to talk about.
If you want to build a protocol with privacy on Aztec, I'm sure you can also bake attribute utility into your protocol, so we can set up.
Yeah, exactly.
You can do it on your own. You don't have to rely on us to provide you with compliance.
But yeah, that's definitely a fair question. But I think there's reasons we have the design decisions we have, and it's definitely something that has to be figured out by the overall ecosystem. But I would just say that there's a stark difference between no privacy and complete privacy. Where the regulators stand, that's kind of not my area of expertise. But I would not say that you can't do some level of privacy on blockchain. Which that's sort of for the app ecosystem to figure out.
All right. Thank you so much. And I think next up, Marek, are we Do we? Are we able to move straight away?
I propose I set up a small team to arrange here things back, but I'm gonna lead you to the next location, which is just around the door. Thank you for coming, Adam. Thank you for joining us today and doing great presentation.